Thank you for having me. I'm super excited to be here. I'm sorry that I'm not there in person, but thank you to the organizers for inviting me and for that lovely introduction. And you're exactly right that the work that I'm going to talk about is very related in theme to the previous work. I caught the end of the previous presentation. And my work is also about using human behavior to understand mental states, in this case, to develop robot algorithms that can assist people. So I work in the space of assistive and collaborative robotics. I think a lot about how robots can work closely with people and take actions that are supporting whatever task a human has in mind, in this case, building a Jenga tower. In order to achieve that, it's important that the robot is aware of what the human is trying to do. So their task-related beliefs, desires, intentions, preferences, all sorts of mental states. And we lump these under this umbrella of mental states. Unfortunately for the robot, these aren't directly accessible to it. But what the robot does get is a variety of different nonverbal and verbal behaviors. I should add emotion here as an homage to the previous talk. We have where people are looking, what they're saying, what choice of action they're making in the context of the task. All of these can be grouped under this sort of general category of behaviors. And these behaviors are directly influenced by people's mental states with relation to the task. And so using these behaviors, my work tries to develop mental state models for the robot that can back out the relevant mental states, the relevant beliefs and desires and intentions in particular, so that the robot can predict what kind of assistance or collaboration people would benefit from. So to put that simply, the focus of my work looks at how we can detect and use aspects of human mental states during collaborative human-robot interaction. And for the purposes of this talk, when I say mental states, what I mean is intent in particular. Intent being the commitment to achieving a particular action, like I intend to reach for this glass of water. I probably don't need to convince this audience that human behavior is a useful signal, but let me humor me while I do. We get a lot of information when people are doing human-robot collaborative tasks from the behaviors that people are exhibiting. So here, this task is for a user to work together with this robot arm. The user is providing some control input. The robot is trying to assist them in spearing a marshmallow off of a plate. So getting a morsel of food and retrieving it. And this is a really simplistic proxy for assisted eating. In this case, our user is not motor impaired in a way that she would actually need this, but she is giving us a great example of all of the different kinds of behaviors that we might expect, including facial expression, eye gaze, body posture. And I'm particularly interested in eye gaze. And the reason for that is because gaze is always present when people are, or I should say almost always present when people are doing a task. It's highly informative of what people are going to do next. And it is a completely intuitive natural signal that people don't have to think about producing. So what you're seeing here in this video is a loop of a real world scene and a simulated scene of somebody's eye gaze as they're doing this extremely constrained manipulation task. So the person reaches for a block, moves it around an obstacle, touches it to to a location, and returns the block to its original position. And the cross represents their actual eye gaze. So you can see how their eyes are skipping ahead in the task that they're doing. So they never, they don't wait. The eye gaze does not wait until the first reaching action is complete before moving on to the next task, which is maneuvering around that obstacle, and so on and so forth. So eye gaze is an extremely timely and relevant signal for us to try to predict in manipulation what people are trying to reach for or achieve. Capturing eye gaze is a lot easier now than it used to be. I'm really, really grateful for the scientists who did this research in the early noughts, because at that time we didn't have the gaze tracking technology that we have now. And so an eye tracking experiment looks something like this, where a person would come in and do this task, but their eyes were being recorded by an external camera. And in order to accurately tell where they were looking in the world, they had to calibrate and then make sure their head didn't move. So people would come in and bite down on this bite bar that would keep their entire skull static while they did this task, and their eye gaze was recorded. Things are better now. We have really great equipment now to record eye gaze. On the left is an egocentric pair of eyeglasses. On the right is a desktop-based eye tracker. We use both in my lab, and it makes our life a lot easier. So we use these trackers, and this is the kind of signal that we get from it. So here you see a first-person view of the same task that you were seeing before, this marshmallow spearing task. The pink dot represents the user's eye gaze. And and here the user is simply teleoperating the robot, there's no assistance. So based on previous findings in the psychology literature about gaze, we expected that people's eye gaze in this task would also skip ahead to the next target of the manipulation, which is, in this case, the target of the spearing, so the desired piece of food, as people were maneuvering the robot arm down toward it. And what we very quickly realized, and you can see in this video, is that that's not really the case. Actually, the vast majority of people's eye gaze is on the robot end effector itself, because that's what they're controlling. And this makes sense. They don't have proprioception for the end effector the way they do for their own body. And so they can't tell where that end effector is in space reliably without actually looking at it. And so our goal of using eye gaze to simply identify the target, the next target of manipulation, turned out to be a little bit more challenging than we had initially thought when we set out to do this task. Not only is the eye gaze often at the end effector, specifically only 16%, we ran a study with 24 participants doing these tasks, these pickup tasks, and only 16% of the fixations that they made, so times when their eyes were resting on certain points, were actually to the goal piece that they eventually retrieved. And in 10% of our trials, we actually got no goal-directed gaze at all. So people weren't looking at their target morsel directly during the task. Now, it's not that they were staring off into space. Most likely, although we haven't tested this, people were using their peripheral vision, which is not detected with a fixation, or memory, because these pieces aren't moving, in order to complete the task. And they didn't need to be looking at where that target morsel was. And so what we have learned from this is that if we want to figure out people's intention, in this case, which target object they're reaching for, we need to account for the fact that the eye gaze is quite noisy and quite sparse. So how do we deal with this? Some of our work has tried to take advantage of the fact that eye gaze is not a single process, but it's actually a temporal sequence of fixations. And we can build a model that accounts for that temporal sequence in order to be better at identifying the target of people's manipulation. And so this model used people's eye gaze and a pretty standard temporal model, which is a hidden Markov model, based on previous data. So we trained an HMM for each goal with the fixation locations that people had exhibited when they were reaching for that goal. And then given a new set of fixations, that sequence was scored based on these pre-trained hidden Markov models for each of the available goals. And the probability of that particular morsel being the one they were going for is proportional to the score that it got from its HMM compared to the others. I thought my student explained it really well, so I'm going to play you a short video where he gives you kind of an overview of this process.
We can see how this model works in detail here. On the left, we have a video of an actual trial with key points and gaze fixations indicated. On the right, we have a plot of the prediction information throughout the trial. The top plot shows the prediction made by our sequential algorithm. It compares that prediction with the prediction made by an aggregate benchmark, which uses only the number of fixations directed towards each goal. The second plot shows the actual sequence of labels. The final plot shows the estimated hidden states assigned by the HMM corresponding to the correct goal. The states of the HMM enable the prediction to account for fixations towards other potential goals, which the aggregate model cannot handle.
So you got to see the process working in real time. So does it work? What was the outcome of this gaze modeling? What we found is that gaze can be good at predicting the goal. On average, the predictions that were made from eye gaze were earlier toward the correct morsel than the baseline. So in this graph that you're seeing, we are looking at the probability that was assigned to the correct goal. I remember we had 3 goals. So the probability assigned to the correct goal, or in this case, 2 goals, as a function of progress through the task. No, I think we had 3 goals in this. Okay, 3 goals, but we have a line at the 50% mark. So the dark blue is our method. It's that sequential data method. The light blue is our aggregate baseline that just counts up the number of fixations to each goal. And the gray is the prediction that we're getting from the joystick, which I'll get into in a little bit of time. So when gaze was correct, it tended to give us a correct prediction earlier than the other 2 baselines we compared it against. However, when it was wrong, it was pretty confidently wrong. And you can kind of see it in the violin plot at toward the end of the trial. The dark blue line has a big mass at the top where it was correctly identifying the goal, and a reasonably big mass comparatively at the bottom where it was incorrectly identifying the correct goal. But it was very confident about that identification. And so what we have learned from this is that eye gaze is a pretty useful signal of intent. And we can detect intent using these sequential models of eye gaze, but it's also noisy and sparse. And it's not a panacea for trying to predict intent. It can be used as one element of a more robust intention model. And so that's what we did next. I talked to you just now about how we detect eye gaze to predict intent. Now I want to tell you about how we use that intent prediction and that eye gaze to actually improve the collaboration between people and robots. So I sort of hinted at this task earlier, but I want to explain it a little bit more now. This is going back to that marshmallow spearing task that you saw at the beginning. I worked with a shared autonomy algorithm that was attempting to assist users in doing these kinds of goal-based manipulations. You can see on the left is a user spearing the marshmallows with the shared autonomy algorithm, helping them out. And on the right is a user purely teleoperating the robot to try to spear a marshmallow. And clearly, when the robot is providing assistance and that assistance is useful, the users receive the food much faster, and we validated this experimentally. The shared autonomy algorithm under the hood is using a POMDP, a partially observable Markov decision process, to keep track of the uncertainty over the potential goals that the user has. So the user is providing a control signal to the robot, you, that in this case is the input from a 2-axis joystick, but it could be any kind of control signal that moves the end effector. That's fed into this POMDP that uses the control signal to first update its prediction of which goal is the one the user is going for. So it updates its belief probability over all of the goals, and then selects an action that maximizes its movement towards as many of those goals as possible, and kind of iterates like that. So the original shared autonomy algorithm only used the joystick signal as the user input. And so my insight was that we could also combine this joystick with eye gaze in order to be better at this goal recognition step. So have better intent prediction, because as we saw, eye gaze can be used for intent prediction. So the same student, Ruben Aronson, took the hidden Markov model that I presented earlier, integrated it into this shared autonomy loop, and we assessed the performance with an in-home study. And so we had users, again, do a manipulation task. In this case, it's a bin pickup task, because we actually specifically created a task that would be challenging for people to do with the robot. We had them do this bin pickup task and compared their performance when the robot's assistance was running the original shared control or shared autonomy joystick only predictions, running goal predictions based only on eye gaze without the joystick, and a third experimental condition, which was the merging of the joystick and the gaze predictions in order to provide assistance. Now, it's worth noting that this study was conducted during COVID, and it was done in a completely COVID safe way, which I think is just really kind of cool, and was a very creative adaptation on the students' part. So for every participant we ran, we being Ruben, delivered a box, a kit, an experiment kit to the participant with a webcam and a computer and our eye gaze sensor. So here you can see that desktop-based gaze sensor and the joystick. They had instructions on how to set it up, and then Ruben would Zoom with them and walk them through the experiment. They would be controlling the robot live in our lab. And so they were able to do this task even when they weren't physically in the same place as the robot. That just kind of shows that this also works not just for assistive robots for, motor impairment where people are local, but also other kinds of remote robot control tasks like bomb disposal or EVAs on a spaceship. So we ran this evaluation of our integrated system, and what we found is that in fact, when we had stable gaze early enough, we improved the assistance that the robot was able to provide the people. So the graph on the left shows the strength of the prediction of the correct bin as a function of the time since the trial started. The blue lines, the blue data points, represent trials where gaze was early, which means gaze stabilized within 20 seconds of the start of the trial. And the kind of gold or yellow lines represent late gaze, and the red data points represent predictions made only with the joystick. So just to give you a sense of the breakdown here, about half of our trials fell into that early category. Another 20% fell into the late category. And then the remaining trials did not have an early or a late gaze stabilization. So you can see that when we have this stable early gaze, the prediction performance improves. You can also see in the graph on the right that the assistance improves. So this graph is showing the amount of assistance in the X direction as a function of centimeters per second over the time since the trial started. And what we were hoping for, and what we see here, is earlier assistance being better. So with early gaze, the robot was able to assist people earlier in the trial, whereas with the joystick-only predictions, the robot was actually providing most of its assistance toward the end of the trial. And so we showed that eye gaze, that a merged method of eye gaze and joystick together could produce this really nice behavior. Oh, I had pop-ups. So earlier prediction and earlier assistance. That was nice. But of course, when you run studies with humans, things sometimes don't go the way you want. And so we found this really interesting problem where the context, the setup of the environment actually caused our system to grossly misunderstand the user's goal. So in this case, the user was trying to reach for the object on the right. The way the interface was set up, they had in the top corner a little diagram of the control mode that the robot was in. And when they looked at that diagram and then looked back at the robot, for whatever reason, the system changed its belief predictions to weight the left goal more highly. And now because the robot is over toward the left goal, the system continues to think that the left goal is the one that the user wants. So these numbers, I'll play the video again, the numbers represent the prediction, the belief that the system has about which goal the user is going for. And you can see that the user is fighting the robot to try to pull it back over to the right. But because it's using eye gaze as its intent prediction, it's going to be wrong just because the robot is nearer to that goal. So like I said before, eye gaze is not a panacea. It's not always going to be goal directed. And sometimes we can get into trouble if we try to rely on it too heavily. So the lesson learned from this part is that if you have attention that is intent being inferred from gaze, you can use that to improve the assistance that you're providing people. You can provide them earlier assistance and more correct assistance in this kind of collaborative manipulation task most of the time. But when the eye gaze is not stable, in those cases where it doesn't stabilize, or in the cases where the setup of the environment is such that the system essentially gets confused, you can actually end up with some pretty frustrating, but also kind of hilarious misunderstandings, let's say, from the robot. So there's much work to be done. I don't know if I've inspired anyone to work in the space of eye gaze for intent prediction, but it's still wide open. There's a lot of work that we can do on really narrowing down when is the gaze meaningful, filtering out incorrect eye gaze, allowing for kind of reassessment of goals and things like that. All of the work I've presented for you today has been in the context of collaborative manipulation. I want to talk very, very briefly about another direction that we're going more recently, which is in the context of assisted driving. In the same way that a robot collaborative manipulator needs to consider what intention people have, what morsel they're reaching for, in assisted driving, an intelligent vehicle needs to consider what or when it should alert a driver to an upcoming hazard. I imagine that some of you have cars or have ridden in cars with these kinds of new alerting systems. If you get out of your lane, it'll start to beep, or if you get too close to the car in front of you, it'll start to beep. The annoying thing is that it will do that no matter what you know. It will always alert, even when you are in control and aware of the situation. So we asked, can we use eye gaze as a measure of what people know about the scene so that our intelligent vehicle is not alerting them needlessly, but is actually alerting only when people's gaze indicates that they are not aware of this hazard. The reason it's important not to alert all the time is because people get alert fatigue. And we see some undertrust occurring with robots when you have too many false positive alerts. So the work that we're doing here uses a VR driving simulator developed by some students in my lab, led by Abhijat Biswas. And this VR 3D driving simulator allows us to track eye gaze in real time. So in this video, you can see eye gaze. I don't know how it looks on the projector. Maybe if you're at home, it looks better, but you can see it as a sort of small red square in the center of vision. And here, this is a first-person view of somebody driving. The question we're asking is, can we use this eye gaze trace to detect what people know, or conversely, what they don't know and what hazards they're likely to end up hitting or they're likely to have an accident with if they are not aware. So we are working on this now. The first sort of major publication from this work was just presented at IV in Intelligent Vehicle Symposium in Alaska a few weeks ago. And that work was really trying to characterize not just the gaze that people, the fixation gaze that people are making when they're doing this task, but also their peripheral vision. Because something that I didn't talk about today, but is actually very important, is that all of the work until now that I've discussed has to do with fixated gaze, but people are using their peripheral vision in tasks like driving all the time. And if we're not accounting for that peripheral vision, then we don't have a complete picture of what people know or don't know about the scene. So this brings me to sort of the end of the talk. I talked about how we can use human behavior, in this case, eye gaze, to provide intent inference, to make inferences about people's intent or people's knowledge in a human-robot collaboration. And that is true, but I hope that I have also shown you that we have to balance that with the fact that these behaviors can be noisy or sparse or misleading, and we actually need much cleverer algorithms than it originally seems if we're going to use human behavior to try to infer mental states. I want to, of course, thank the students and collaborators who are involved with this. They do all of the actual work, and I just get to brag about it in front of audiences. And I'll leave you with these 2 points that are about how we detect and then use eye gaze to inform intent inference in human-robot collaboration. So thanks for your attention.
Thank you very much for your talk.
I don't have the chat up, so if there are questions there, the organizers can just read them.
Okay, it looks like we have a question from someone in person. You can tell your name and your question. Go ahead.
Yeah, hi, Henny. This is Rachel Burns, and thank you for your very interesting, what you've covered today. I wanted to ask you about what you mentioned right at the end. You were saying that we need to consider the peripheral vision as well. And I was just wondering, how can you identify peripheral vision? Like, can you detect that with the eye tracking technology?
So that's an excellent question. Right now, the short answer is no. The way the eye tracking technology works, it really focuses on foveal vision, the center of your vision, and providing a single point. However, from the center of your vision, we can start to infer, where your periphery might be. Although again, that's not as easy as we thought. So my student did this analysis of peripheral vision during a variety of tasks, and it turns out that your periphery grows and shrinks. It's not a constant size. It's not like we can draw a circle around your center of your vision and say everything within this you're perceiving in your periphery. And it's affected by how recently you saccaded, so how recently your eyes moved from one place to another. And so we showed that immediately after a saccade, within the first few hundreds of milliseconds, people are more likely to miss things in their peripheral vision than they are as they've been fixating on a point longer. And this sort of matches what the psychophysics literature tells us as well. Something interesting that we found is we did this task both in the driving simulator, so while people were doing a driving task, and in VR, but in an extremely basic, like very classic psychophysics task where you have to fixate on a cross and a probe appears and you press a button. So no distractions, no other visual input. And what we found is that in the driving task, there's also, on top of that, a very distinct bias towards the lower down stimuli. So stimuli that appeared high up in the visual field were less likely to be perceived in periphery than the stimuli that were lower, but we didn't see that in the clean room psychophysics task, which means that not only is periphery affected by saccading, it's also affected by the context of what it is that you're doing at the time. So it's a really interesting question, and we're hoping to keep exploring it.
All right, thank you for the answer. All right, do we have any other in-person questions? Okay, going once, going twice. I think that's all for in-person for now. I think we have some virtual questions.
Hi again, Henny. Thanks for the great talk. So during your talk, you show that example of a person trying to correct the gaze so that the robot would correct like the trajectory and I guess not doing the right thing because it's looking for the goal. And that made me think whether you have any thoughts or work on having robots like instruct humans how to provide better gaze cues or give humans in what they're thinking so that they improve interaction.
Yes, great question. So yes and no. So I definitely have thoughts about getting having robots behave in a way that elicits better information from people, but not for eye gaze. And for eye gaze in particular, the reason that I don't want that is because my goal is to use the natural eye gaze that people are emitting without thinking about it as they're doing the task, rather than forcing them to think about where they're looking and what they're doing. So there are plenty of gaze-controlled robot systems. They're kind of amazing and they work really well, especially for people with severe motor impairment who don't even have access to a joystick. But those systems trap the eyes. The eyes become a remote control, and you need to then control the robot with your eyes, which is not what we're trying to achieve. So for gaze, I actually don't want the robot to interfere. And in the video you saw, that participant did not know that the robot was using their eye gaze to make its intent inference. We didn't tell them what condition they were in during the study. And so their eye gaze is just what they would have done. But I do think in terms of HRI that the idea of having the robot teach the human how to be more informative is a really, really interesting question. That's a whole other talk, but you can absolutely take actions, the robot can take actions that lead the human to providing examples, for instance, that are maximally informative. This is active learning. And I know you heard from Scott Neekum earlier, and we had a paper published together a couple of years ago on this kind of active learning from human feedback and the different ways robots can achieve that.
Thank you.
So Henny, so I have another questions. So this is about what kinds of goal you could actually infer from gaze. So human intention is pretty broad. And we imagine maybe there's some kind of goal you probably cannot infer from intent. And then a similar, I guess, related question would be for gaze, right? What kinds of tasks you can actually, what kind of tasks can actually benefit from, intent prediction based on gaze?
Yeah. Excellent question. Yeah, you picked up on one of the interesting limitations of this work, which is that we have to carefully select the tasks such that the gaze is meaningful for task completion, and we can infer intent. So I showed you two tasks. I focused mostly on this collaborative manipulation task. Eye gaze in manipulation is extremely informative about the task. Psychologists have known for a long time that when you're doing a physical task with your hands, you almost never fixate on anything that doesn't have to do with the task that you're immediately doing, and that your eyes will do this very reliable kind of jumping ahead to the next target of manipulation. And so we can use that gaze information very reliably in manipulation tasks, which is why we tried this first in this collaborative manipulation domain. Similarly, when we're doing the driving, we're not using the eye gaze for predicting, where somebody wants to go. We're not predicting intent, we're predicting knowledge, because in that driving task, our eyes are used to gather information. And so, there's some correlation, although it's not perfect, between what we're looking at and what we know. So you have to pick the task such that what you're trying to get out of eye gaze is actually being used is being exhibited in that task, if that makes sense. And yeah, there are intentions and tasks that we can't identify. So yeah, eye gaze is for sure not the solution in a lot of those other collaborations.
Right, so that makes sense. So maybe like a brief summary about what you said. Like one type of could be information seeking, like the inner driving, if I understand correctly. Another could be maybe like manipulation or control that requires visual inputs. Does that sound about right?
Yeah, that sounds good. Yeah, as you were asking the question, I was trying to think of like an umbrella concept that I could
Right.
provide. I can't think of one right now, but I think it would be interesting to try to formalize that a little bit and say, like, is there some overarching feature of these tasks that we can say make them amenable to gaze-based collaborations?
Right. Got it. Right. Thanks so much.
Yeah, thank you for the question.
Thank you, Henny, for the wonderful talk. Let's thank the speaker once again.
Thanks, everyone. Oh, I can hear that. That's good.
Okay.